The purple object is going to get a boost from the green one right here, and it's thrown from the system. That doesn't come back. This was actually one of the shorter time scales for an ejection, but this is quite remarkable because this wouldn't happen without the mass accretion term. Having that extra mass being added to each clump in the system based on its position adds, like I said, an extra dynamic to the behavior. And these ejections actually turned out to be very common. I ran 200 simulations for the study, and 129 of those resulted in an ejection of one of the objects, one of the clumps. And I'll show you the results of those simulations there. So here's the mass distribution we got. You see it's peaked at about 10. That's a log-base 10 on the bottom axis there. It's peaked at about, I don't know, 1.05. It's about 10. But they didn't gain very much mass. Their ejection velocity, about 3, peaked at about 3. That's a little bit more than Dr. Basu found, and I think we can attribute that to the fact that these were point masses we were dealing with. They're not being succumbed to drag force like you would in a dust cloud, and they can get much, much closer to each other and gain much bigger of a boost. We also looked at the time to ejection. They're ejected fairly early. You can see the peak there is in the 0 to 0.25 range, and we also fit a exponential function to this of that form. And we found the ejection lifetime to be about 98,000 years. So this just reinforces our view that it's a very common event and it happens quite quickly. The system does not want these clumps to stay in there. It's a very unstable region. Sorry, let me go back. You might think that the longer an object is in the system, the more mass it's going to have. Well, in general, maybe, but that's not always the case. And you can see with this graph here, there's a steady line at about 10 Jupiter mass of objects that are ejected at that mass, even up to 4 times 10 to the 5 years, which is a very long time to be in the system and not gaining any mass. And here's a good reason for it. This is an a trajectory plot of one of the simulations that I ran, and that dashed line is one of the clumps that got sort of thrown from the system fairly early and spent a lot of its time out there about the 6,000 astronomical units range. It's very far from the center of this, central object rather. And then it comes back, gets thrown around a bit and gets ejected from the system. The gray line at the bottomish area is the central object with the other mass going around it, and there's quite a bit of drift going on there, and that's also a consequence of the mass accretion term in the inline code. So what did we find? Comparing to Dr. Basu's work, we have a mass about 12 Jupiter mass, 9.8 to 15. It's not very comparable to 80 to 350 Jupiter mass, but keep in mind that the 80 is the mass of the clump that's ejected, not the final object. So this is still qualitatively the same sort of idea. We're getting these ejections of these low mass objects. Velocity, 2 to 5 kilometers per second compared to 0.8. I already gave reasons for why that's a bit bigger. Time to ejection, 98,000 year lifetime. And this is the time from when we start the simulation to when it's ejected. We're not paying attention at all to how those clumps form. We're just saying, okay, those clumps are there, what happens? I want to say about a 50% ejection rate. This just comes from the fact that I ran 200, saw 129 ejections. Of course, that's greater than 50%, but if we were to run many, many thousand more of these simulations, I'm confident that it would converge on 50%. So this puts an upper estimate at 1 to 2 ratio of brown dwarfs to stars that we might expect to detect in our galaxy. So what sort of work is going on to detect these things? There's the WISE Wide Field Infrared Survey Explorer at NASA. And they're looking at brown dwarfs in the region of our sun. This is a plot that they gave on their website. You see the sun, there's that little speck. All those circles are brown dwarfs that they've detected. One in particular, Dr. Michael Cushing from the University of Toledo came to talk at Western about this object here, and that's a wide dwarf, a very, very low mass, very, very cold brown dwarf. Green just because that's the filter that was given to the detector. Now, it's so cold, in fact, that if we were standing in the atmosphere of that brown dwarf, it would be colder than the air temperature in this room right now. And that led to some pretty clever titles for news articles. Give me that one. That was really amusing. And NASA also tried to chime in there. So, conclusion. Ejection events are fairly common. Qualitatively, we've shown between my work and Dr. Bass's work that these ejections do happen, and they do have a mass of that of the brown dwarf. My work put an upper limit, I'd say, at 1 to 2 brown dwarf to star ratio. The WISE survey suggests 1 to 6, a little lower than what we found, but there's a lot of work still to be done. still to be done. There's a microlensing survey that actually was done recently that looked at objects in the halo region of our galaxy as opposed to the sort of local stellar region that WISE worked on. And they suggest 2 to 1, which is large. It's kind of ridiculous, actually. But they also included high-mass Jupiter-like objects. Maybe not brown dwarfs, but still, it raises the question, what's going on? What do we not understand? There's still a lot we still don't know. And it's a very exciting time for both theoretical and observational astronomy because, one, we need to detect these things. We need to get a good estimate of how many there are out there. And theoretically, we need a good model. So future work would be developing a more robust model with more variables to the simulation and go from there. Thank you. Sorry, I'd also like to thank Dr. Basher and his research group for their comments on my talk, the Department of Physics Astronomy at Western, the Science Student Council at Western for the financial support for me coming to this conference, and NSERC for funding my research, and of course, UBC and the CBC people for organizing. Thank you. Yes?
Sorry, I think I got confused early on. So are you saying that the clumps you've injected are brown dwarfs, or the brown dwarfs like are not stars because they lost clump mass during formation? What does the clumping tell us?
The clumps that are ejected are just sort of a consequence of the disk fragmentation, but when those clumps go through their process of core collapse, the final mass of those clumps should be in the brown dwarf range. That or low mass, depending on how large the clump mass was. Because remember, the upper bound was 350 Jupiter mass. Even at a half, even if the resulting mass of the object that forms from that clump is at a half of that, we're still in the low mass star region. So
it's when the ejected clump collapses that would form a brown dwarf.
That's right.
Okay.
So I got 2 questions. So the first one is, so you said that brown dwarfs doesn't support fusion. So does it have any sort of energy generation mechanism?
It does fuse. They haven't found to fuse deuterium and lithium, but that's not.
Which is how we do fusion on Earth if we were to do it, right? Like,
I'm not sure.
Okay, I don't know. Sorry, keep going. Yeah.
The key is that they don't fuse hydrogen. That the fusion of deuterium and lithium is not enough to make them very different.
Okay, and second thing, so can you go back to your 3-body simulation? It's a pretty good animation. The previous one, actually the one that's moving.
Yeah.
Yeah. So the green one is the one that didn't get ejected, right?
That's right.
So what would it become?
Sorry.
Would it become what would it become if it's not ejected? The green body.
Either it would be absorbed by the central object, or just the mass would be redistributed. Where these are point masses, so we're not taking into account the dust effect. Or it'll form a binary system with that central star. And these have been detected, binary brown dwarf star systems. And this could also.
What did you say your initial density was? You said it was 0.1 solar mass?
The initial mass of the central club was 0.1 solar mass, yeah.
Okay. And your distribution of the surrounding dust was what?
I didn't use that at all in my code, but I can show you. That was the distribution of the dust mass. That we sorted.
Okay. It's observed to be somewhat similar to this?
Yeah.
Okay.
No?
That was one more talk.